Hello everyone, welcome to the course on electromagnetic theory and interference. In this session, let us see about the transmission line characteristics. In the previous session, we have seen the transmission line, which is going to be the lossy one, okay, where the conductors are imperfect as well as the dielectric also imperfect. Now we are going to consider two special cases. One is lossless line, which is useful for power transmission, and other one is distortionless line, which is useful for sending the telephone signals. Now let us see what do you mean by lossless transmission line. Transmission line is said to be lossless if the conductors with which the transmission line are made of are perfect conductors, that is conductivity is approximately infinity, and the dielectric medium is lossless. So conductivity of dielectric medium is zero. So we can see here the primary constants of the transmission line R, L, G, C are computed for three different types of transmission line: coaxial, two-wire, and planar line. And from here, if you apply this condition, okay, conductivity is infinity. So we can see for R, it is inversely proportional to conductivity of the conductor. So we get R as 0, since 1 by infinity is 0. Similarly, if we apply for G, for the conductivity of the dielectric medium, so everything turns out to be 0 for G. Okay, so here the L and C component does not have the conductivity parameter. So R and G both are equal to 0 in lossless line. So for such a case, we are going to find how will be the attenuation phase constant. Okay, that is propagation and characteristic impedance. These only we are targeting, as well as velocity of the line. So first let us see that R, G both are 0, right? This is a necessary condition for the line to be lossless. If we apply this condition here, Rg is 0, so these are the real part. So the real part 0 means attenuation is 0, where the imaginary part is the, so alpha is 0, so gamma is going to be j beta only. That is going to be j omega into root of LC, okay, from this expression. Velocity is omega by beta. Beta just now we have found it is omega root LC. If we substitute that, omega get cancelled, we get the velocity as 1 by root LC. And this velocity can be equated to frequency times the wavelength. So if we apply this Rg as 0 in the characteristic impedance, so here this real part gets cancelled. In imaginary part also j omega get cancelled. Then we get only root of L by C. So that is characteristic impedance is purely resistive in nature. The reactance part is 0. Now let us see about distortionless line, where this condition R by L is equal to G by C. So before going into that, we should know what is distortion first. Normally, a signal consists of a band of frequencies. The wave amplitude in that band of frequencies, okay, wave amplitude of different frequency component will get attenuated differently in a lossy line. Because we know that attenuation is frequency dependent parameter, and general phase velocity of each frequency component also it's a frequency dependent one. Since attenuation and phase velocity all are frequency dependent, it will lead to distortion. A distortionless line is a one in which attenuation constant should be frequency independent, and the phase constant should be the linear dependent on frequency. So this is a condition for distortionless line. R by L is equal to G by C. So if you substitute this particular condition in propagation constant, so before substituting that we have to take R common from this factor and G common. So we can replace L by R by C by G. So in that case we get same term here. So root of Rg into 1 plus j omega C by G. And from here we can find attenuation constant is root of Rg, and phase constant beta is going to be, if you simplify this, root Rg into C by G. Okay, we have to simplify it and we will get this answer, root of omega root LC we get. From this relation we can find that attenuation is independent of frequency, but phase constant is a linear function of frequency. This is a condition we have applied for distortionless line. Let us see about the characteristic impedance Z naught. Similarly, we have to take from this expression R and G as common from the numerator and denominator, and we can replace L by R by C by G. In that case, both the terms will be same and it get cancelled. So we get root of R by G. Similarly, if we take L and C as common outside and we simplify it, we get root of L by C. So anyway, the impedance is going to be only the resistance part. Okay, the reactance part J X naught is 0 here. Resistance part only is going to be either R by G, root of R by G, or root of L by C. And this velocity is omega by beta, and since beta is same as for lossless line, we get velocity as 1 by root LC, which is equal to frequency times wavelength. We can conclude that both the velocity as well as the characteristic impedance are the same going to as compared to the lossless line. Here we got additionally root of R by G, but there R and G are 0 in lossless line, right? So we get only root of L by C for the impedance part. A lossless line can be a distortionless line, but distortionless line cannot necessarily be a lossless one. This is a very important point to note. And lossless line, as I said, it is helpful in power transmission, but distortionless lines, we can use it for telephone lines. Here we are summarizing all the three cases. The first, the general case, that is lossy transmission line. For that, propagation constant and characteristic impedance is mentioned. If you compare lossless and distortionless, in terms of propagation constant, the attenuation is 0 since Rg is equal to 0 in lossless. But in distortionless, we get the factor root Rg, and this phase constant term is going to be same, omega root Lc. And if you see the characteristic impedance, we saw that for lossless and distortionless, both are equal to root of L by C. Whereas for distortionless line, I can equate to root of R by G also. Okay, but that I can't do for lossless because Rg value is 0 in lossless condition. So hope you understood how we derived these special cases, lossless and distortionless transmission line, from the general lossy transmission line. Hope you enjoyed the session. Thank you.